Envision an immense asteroid hurtling towards Earth. As you observe this movie, is it possible for us to evade a catastrophic event of immense magnitude? Or are we powerless in the face of celestial influences? These critical questions pushed NASA to fly a specially built probe straight into the asteroid's path. However, the outcomes defied expectations. What unforeseen plot developments occurred? What are the ramifications of this for our safety? Join us as we delve into the perplexing phenomenon of an asteroid collision that has left NASA experts astounded and unable to provide a definitive explanation for its occurrence. Prepare for an exploration of the captivating voyage and the unveiling of enigmas beyond the cosmic boundary. Engineers and scientists have devoted their efforts for years to constructing a probe with a specific objective: the purposeful destruction of NASA's Double Asteroid Redirection Test, DART. The purpose was apparent from the start. As it had a short lifespan, the spacecraft was created with the express purpose of assessing a new planetary defense method. It was designed to be a comprehensive solution specifically aimed at two near-Earth objects called Dios and Doros. Dios, a Greek term denoting twin, was detected on April 11, 1996, by researcher Joseph Monani utilizing the Spacewatch telescope at Kitt Peak National Observatory in Tucson, Arizona. Scientists hypothesized that Doros might have a moon after they detected odd echoes in the data from NASA's Goldstone Solar System radar in the Mojave Desert near Barstow, California. They got more certain about it by looking at how bright Doros appeared over time using telescopes. They also analyzed radar photographs taken by the Arecibo Observatory in Puerto Rico on November 23, 2003. As Doros and its moon revolve around the Sun, they get close to Earth's orbit, occasionally coming fairly near to us. In 2003, Doros got as close as 0.048 astronomical units, AU, to Earth. 1 AU is the distance from the Sun to Earth. Although these asteroids don't pose a hazard to Earth, NASA picked them for the special DART mission. It's NASA's first mission to check a new technique to defend our planet. The technique involved the probe's rapid collision somewhat decelerating Doros' orbit, leading to a lasting shift in its trajectory. However, the issue in this planetary defense technique comes not just in manufacturing the probe and colliding it with the asteroid, but in precisely determining the impact intensity. The purpose is to dislodge the asteroid just enough to steer it into a safe orbit. This precision is vital. When discussing asteroid defense, detonating these rocky asteroids may cross one's mind. Planting an explosive charge on an asteroid or deploying it within, analogous to situations in movies like Armageddon, seems theoretically plausible. However, the underlying issue resides in the aftermath of such an explosion. The resulting detonation would spawn several asteroid fragments, each following unpredictable trajectories and potentially posing a renewed threat to Earth. While humans might succumb to such dramatic tactics in grave crises, research advocates a more realistic approach. Instead of devastation, the focus is on moving asteroids out of collision trajectories or tugging them away. Depending on the location and time of danger detection from space, a relatively minimal effort may be sufficient to divert an asteroid into a safe orbit. Yet, the margin for error is tiny, as an insufficient or excessive push might leave the asteroid still posing a hazard. This highlights the necessity of NASA completing the process on Doros, an asteroid positioned sufficiently far away to avoid any potential hazard. Regardless of the test conclusion, the nightmarish scenario of a big asteroid hitting Earth is unsettling. The immediate destruction of the impact zone would be catastrophic, and the entire fabric of society could face a protracted demise due to the aftermath. The effect would be severe tsunamis, flames, atmospheric dust, poison, and unexpected chain reactions from subsequent natural calamities. This series of events replicates the horrific fate the Chicxulub asteroid imposed on the dinosaurs millions of years ago. Imagine a massive asteroid as large as a whole mile coming into Earth at 30,000 miles per hour. The energy it brings is like setting off a huge bomb, a staggering 1 million megatons. To appreciate how devastating this may be, let's consider a lesser version. Imagine an asteroid the size of an ordinary home hitting Earth at the same superfast speed. It would release energy similar to the bomb dropped on Hiroshima, roughly 20 kilotons. Buildings composed of solid concrete within half a mile would be flattened, and wooden structures within a mile and a half could be destroyed. This would do severe damage to any city it hits. Now, think about an asteroid as massive as a 20-story building, each side measuring 200 feet. This space rock could carry as much energy as the biggest nuclear bomb today, between 25 to 50 megatons. If it crashes, it might flatten reinforced concrete buildings within a 5-mile radius. In fact, it might entirely demolish most significant cities in the United States. For a space rock to cause widespread harm on Earth, it must be huge. Scientists think that an asteroid roughly 7 to 8 kilometers broad would do the trick. If such a gigantic asteroid slams into our planet, it will cause a catastrophic series of events. The impact will cause a massive dust plume that covers the entire Earth, shutting out the sun and causing a considerable rise in temperatures at the point of impact. This kind of event would lead to the loss of billions of lives, and much of the planet's biodiversity would be annihilated. However, experts believe that some living forms might survive even in the face of such a cataclysmic disaster. According to NASA scientists, it would take an asteroid a whopping 60 miles wide to eliminate all life on Earth. Together, a genuine historical example of an asteroid impact occurred on June 30, 1908, when a 40-meter asteroid slammed into the Tunguska area in Siberia. This hit damaged a wooded area similar to the size of London, distinguishing it as one of the most destructive asteroid impacts in modern history. Recognizing the potential hazards asteroids pose, the United Nations recognized June 30th as International Asteroid Day in 2016. This day attempts to raise awareness about the risk of Earth colliding with asteroids, which are countless celestial entities drifting in space. Scientists, astronauts, and celebrities join on Asteroid Day to highlight the hazards our planet faces from asteroids that cross Earth's course. These events underline the current vulnerability in our space defense systems against prospective asteroid strikes. Discussions on science fiction scenarios and potential answers take center stage in the face of prospective threats, emphasizing the necessity for continuing research and preparedness. Recognizing the magnitude of this threat, international experts and governments worldwide have chosen to begin a comprehensive global asteroid defense program. However, adequately defending against asteroids poses a formidable problem for various reasons. Asteroids are deadly and elusive, emerging suddenly or shifting their orbits due to cosmic events. In the worst-case situation, we only have weeks or months of warning before an oncoming disaster. To combat this, researchers globally constantly monitor all known asteroids and comets near Earth around the clock. Any slight alteration in orbit is painstakingly analyzed, and in crisis, NASA releases an asteroid warning. In the last 2 decades, there have been 3 such warnings. Fortunately, we just dodged tragedy each time, as heavenly bodies missed Earth by several tens of thousands of kilometers. However, relying on chance is not a viable strategy for the long term. Experts worldwide concur that in asteroid defense, there are only 2 possible approaches: violently moving the asteroids out of their orbit or towing them away. The DART mission aimed for Doros exemplified the first method. NASA launched DART in 2021. The mission's purpose was to crash the DART spacecraft into Doros, a near-Earth object, NEO, in order to test a revolutionary strategy for planetary protection. Should the kinetic collision be successful, Doros' orbit would be permanently modified, and it would slow down slightly. Indeed, even modest adjustments to an object's orbit over time can have enormous long-term implications. As indicated previously, Doros by itself does not harm humanity, but in principle we might identify a threat years before it reaches Earth and reroute it far enough away from us to miss us totally. The DART project is a collaborative effort combining NASA's Johns Hopkins Applied Physics Laboratory and international partners from Italy, Japan, and the European Space Agency. The double asteroid component derives from Doros being in a pair with a bigger asteroid named Dios. Doros, a tiny moon-like rock, surrounds Dios, the larger asteroid. It takes Doros roughly 11.9 hours to complete one orbit around Dios, staying around 1 kilometer away. The complete system goes around the Sun once every 2.1 Earth years. In October 2022, it approached close to Earth, roughly 10.6 million kilometers distant, the nearest since 2003 and the optimal time for the DART mission. DART is fairly basic compared to other space probes. It's approximately the size of a refrigerator and weighs only 610 kilograms. It is substantially lighter than Doros, which is expected to weigh roughly 5 billion kilograms. It is also equipped with a camera dubbed Draco, short for DART's reconnaissance, and Asteroid camera for optical navigation, sensors, and an autonomous navigation system. It also has a small partner spacecraft, LICIA Cube, made by the Italian Space Agency, ASI. LICIA Cube includes 2 cameras, Luke and Leia, that filmed what happened when DART impacted Doros. Launched on November 23, 2021, by a SpaceX Falcon 9 rocket, DART spent the following 10 months journeying in space. Just before the collision, when it was 990,000 kilometers away, DART's navigation system took over. 90 minutes before the disaster, its clever NAV system mapped the final course. When DART was 24,000 kilometers distant, Doros showed up on the camera, taking up 1 point for pixels. As DART swiftly approached its target at a breathtaking speed of 22,000 kilometers per hour, the celestial splendor of Doros and its prospective impact location unfolded before our eyes. Doros was captured at just 3 seconds before the expected collision. The image vividly displays Doros as a loose cluster of debris, a cosmic remnant from the solar system's early days. This spectacular snapshot stands as DART's final transmission, snapped at a distance of 12 kilometers just 2 seconds before impact. Providing scale, each pixel corresponds to around 3 centimeters. The final percent image carries a special charm, as the download was abruptly halted by DART's scheduled dismantling. Strangely, this fragmentary photo has become many people's favorite in the collection. It encapsulated the thrilling and passionate moment when DART ended its 17.5 million-mile journey in the blink of an eye. Throughout its journey, DART demonstrated extraordinary precision, a credit to NASA's brilliance. The complete video, exhibited as a time-lapse of the final 5.5 minutes, exhibits times of blurring caused by the firing of DART's ion engines, producing vibrations in the spacecraft and its camera. The sheer quickness in hitting such a little target is amazing and astonishing. Some shots remain in focus, as the camera has to adjust to the swiftly approaching item rapidly. For those eagerly anticipating the outcome, be assured, the impact was indeed successful. The early findings are better than expected. NASA hoped for a change in Doros' orbit of at least 73 seconds with DART's impact. Surprisingly, the data suggests DART lowered Doros' orbit by 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes. Even with a margin of error of plus or minus 2 minutes, this is 25 times better than NASA's target. It's a tremendous success. The hit created 19 gigajoules of energy, equivalent to approximately 5 tons of TNT. The impact cut out a crater on the asteroid surface up to 150 meters broad. This was an astounding effort since the original size of the asteroid was barely 160 meters. The question arises, why did the impact result in a shortening of Doros' orbit? The explanation lies in orbital mechanics. The collision moved Doros closer to Dios, speeding its orbit. This conclusion was corroborated by observations from optical telescopes on Earth, notably the Southern Astrophysical Research Telescope in Chile. The telescope also obtained extraordinary photographs, such as a breathtaking photograph revealing a 10,000-kilometer trail of debris 2 days post-impact, resembling a comet. The unique feature of Doros as a 2-asteroid system allowed scientists to track Dios' orbit speed. They did this by studying oscillations in brightness when it passes through the shadow and emerges in front of its parent asteroid. This information, acquired from examining the light curve, was further corroborated by radar data collected by California and West Virginia observatories. While DART was a major spectacle of the event, it was not alone. The closest photographs of the collision area were acquired by LICIA Cube, revealing remarkable details. LICIA Cube disengaged from DART 2 weeks before the impact to do its flyby using its self-guided navigation capabilities. Just 2 minutes and 45 seconds after DART impacted, LICIA Cube passed by Doros to capture photographs of the impact site, capturing the evolving plumes and ejecta. In this dynamic photograph, Doros is visible after the impact, with Dios appearing overexposed in the foreground. Take note of the huge plumes of material emanating from Doros, some swirling like vine tendrils. This shows a change in direction as the plume developed, potentially influenced by the asteroid's composition. Similar patterns have been observed in impact testing on fine sediment mixed with coarser material. In another, more distant view also after the DART impact, LICIA cube, along with Earth-based and space telescopes like Hubble and Webb, observed the aftermath. Hubble's photos showed expanding plumes and bent rays from the asteroid, while Webb provided dramatic infrared images of spiraling plumes. Scientists will analyze this data further, with the European Space Agency's Hera mission set to launch in October 2024 expected to advance the study. Hera will investigate the crater and deploy nanosatellites to explore the asteroid's internal structure and momentum transfer. Overall, DART's mission has made significant strides in asteroid deflection technology, proving that we can alter asteroid trajectories to protect Earth. This success highlights the importance of global collaboration in planetary defense and lays the groundwork for future strategies.